I welcome you again on this NPTEL online course on earthquake geotechnical engineering, and we was discussing soil interaction. So, this is the second lecture on SSI. We are under module 3, that is the second chapter of module 3, which is on SSI, and in this chapter these are the topics which we are going to talk. We already discussed 4 of these topics and 3 last direct and substructure method, general steps for linear SSI analysis, and recent advances in seismic soil interaction. We are going to talk about that. So, let us talk about this. First, direct and substructure methods. There are 2 ways of carrying out the soil interaction analysis. The finite element FFM is stand here. The free field motion is applied at the fixed boundary at some distance from the structure. Both soil and structure are considered together in the direct method, and advantage is that nonlinearity of the soil can be considered. While in the substructure method, the 2 systems, foundation subsystem including soil and structure subsystem, they are considered separately. So, it is here. So, direct and substructure method. The first one, this side, this is the direct method. So, the first one is, this is basically direct method up to this one. Here you are considering the whole system together. That means you are considering both structure as well as you are considering the foundation part together. But in the substructure method, you separate out the foundation part and the structure part. So, what is done here? You have the free field motion one, and the top of it. Normally what you do, you replace this free field motion this with some spring and dashboard, which is done here. So, this is this one plus this structure, or in fact because the structure is completely here. So, this will be kind of a scattered motion where you have excavated part, but what we do for the analysis, we do not consider excavated part because it is difficult to deal. We consider the free field which was the given in the first case. So, these are the direct and substructure method. Now, suppose you need to carry out the linear soil interaction analysis rather than nonlinear, then it may be little simpler compared to nonlinear analysis, and how we carried out the linear soil interaction analysis has been discussed here. Here in the case, undersys can be in 3 steps. Obtain the motion of the foundation in the absence of the superstructure, that is the first step. That means you consider the foundation on the top of it, there is no superstructure, and this foundation input motion includes what we call the translation as well as rotational components. Determine the dynamic impedances, the second step. So, let me explain it here with the figure. Your complete problem is given in this case the whole system. In the whole system we have, let us say, piles, and the top of it you may have the pile cap, and then on that superstructure is there. So, when this system is subjected to seismic waves, how to analyze this system? We can divide this problem into different components, and what we are doing, different component that can be only for the linear case, where you consider the soil as well as the structure properties are elastic or they are no nonlinearity is considered. So, in this case, when you have the free field motion here, let us say first step is free field motion. In case of free field motion, the waves are coming, seismic waves are coming from the ground, and there is a no foundation, no structure, and you consider the motion which is coming at the ground as a free field motion. So, let us say this is your input given at the base UGT, UG, EI omega t, while the output is the amplitude in the output is UFF. Naturally, E omega, EI omega t for harmonic excitation will remain same, of course there could be some phase lag. So, this is called free field motion, or in the short we called it FFM, free field motion. Now, if suppose I insert the piles or foundation inside the soil, then even for the same input motion which was the case earlier, output at the top of this foundation is different than you got without the presence of the pile. And as we discussed earlier, you get a rotational component, even your input was only translation, but in output you get translation as well as rotation, and this is called what we call the kinematic interaction. So, this effect of the presence of the foundation in the system is kinematic interaction. So, in this step what we have got? We have got the input is applied at the base of the structure and output you are getting at the top of the foundation this without considering the building or structure. Now, the second step is this after completing first step, we find the impedance functions or what we call the dynamic impedances, which is basically dynamic stiffness of the system, and for that you apply, this is your foundation the soil foundation system, you apply the load on the top which may be translation rotation and you find the response at the same point. So, the load divided by the response will give the stiffness. So, stiffness components are Kx, Kxry, Kxry, Kry. So, these are the components here, spring constants, and these springs you find out for the case when you apply the load from the top. Now, you have motion at this fix at the top of here, and you are defining these spring constants at the same points. So, now here the whole system which was given here in this case, the first case the whole system is simply replaced by what we call the combination of spring and dashboards. So, you have the superstructure as it is M1 K1, where K1 is the stiffness of the superstructure was the case, M naught is the mass of this here. The soil and foundation, soils and piles are replaced here by springs, which is Kx in the horizontal direction, Kry in the rotation and cross coupling. So, you have one displacement and rotation. Here these are the spring constants. In this case spring constant it is only spring, but you can also consider the dashboards, and at the end of these springs the motion applied is the same which has been obtained in the first step, which is kinematic displacement and kinematic rotation. So, these springs are subjected to the kinematic displacement and rotation, and then we analyze this system, and you know that analyzing this system is much easier compared to what we do. It can be done because it is a discrete system which consists of the springs, and but because the superposition is assumed, this technique will be applicable only for linear analysis. Now, for the linear analysis, depending on the type of damping which you consider metal damping, it could be either viscous damping or static damping, then we can define dynamic stiffness or dynamic impedance function, which is because it is a complex number. So, it is denoted by K star, star is denoting that it is a complex number, and this can be easily proved. How this equation have come? This equation is coming directly if I equation of motion, I write equation of motion, let me write equation of motion here. Equation of motion is mx double dot plus cx dot plus kx equal to, I say p naught e I omega t. If I represent x equal to x naught e I omega t, then from both sides e I omega t will be cancelled out, and I will left that k star is kst, where k star is nothing but in this case will be p naught amplitude of the force divided by the amplitude of the motion. So, k star is simply define this and you can find the value of this stiffness kst minus m omega square. You see in this equation for dynamic stiffness you get both real part as well as imaginary part. This was the case when the form of the damping considered in the system is viscous. Instead of viscous damping, if I consider static damping, in that case my equation, because this damping you will have minus this inertial force, and then you have the spring constant including the effect of damping. So, if effect of damping is clubbed with static stiffness. Now, because both the equations are like coming in one case we have viscous damping and static damping. Comparing both the equations you can find out what is relation between C and zeta. Here C is damping coefficient, while zeta here is damping ratio, static damping ratio. So, if you compare, then comparing these two terms, because other terms are same. So, just you need to compare this this term with this term here, and this comparison give you I kst. So, C is equal to twice zeta omega kst. So, that means damping coefficient here in this case is static damping ratio and static stiffness. It will depend not only damping ratio, but it will depends on static stiffness as well as your omega. Omega is frequency of excitation. So, the value of C will keep changing at with the frequency, because it is coming in this equation. In general, dynamic impedances K star are may be represented in the form K star equal to K1 kst, K1 plus iota K2, where K1 and K2 are nothing but real and imaginary parts of the stiffness. Significant advancement has been made in SSI studies in last 3 decades, and what are the advances made in, because there are advances in computer technology. Now it is possible to model the analysis SSI problems more rigorously. Most of these advances are on 2 major and very important issues. What are those issues? One is related to basically modeling of the soil, and another is related to considering the nonlinearity of the soil. So, the 2 issues which are considered are listed here. Though the soil is an unbounded domain, still its precise modeling is possible, because computer advancements are there and the modeling part is taken care of. The behavior of soil during strong excitation is highly nonlinear, and for saturated loose sands even the liquefaction may also occur. However, still today no commercial software such as SASI, Flex, Flex 3D, Dyna, Plexus 3D adequately deals with these important issues, and fortunately our research group including my PhD students Imani, Sarkar, Saeed and later on Firoz work extensively in the area of SSI and soil pile structure interaction. The journey, my journey for SSI started from 1997 from PhD thesis which was submitted in 1997, where in this as for SSI material and geometrical nonlinearity in the theory by Kenya and Kozol, which is a publication of 1982 for pile dynamics, was introduced. Then later in one of the postdoctoral report that is Maheshwari 2003, Kelvin elements was used to model the boundary and his soil model to deal with nonlinearity. Then at IIT Roorkee, my PhD students carried out, first PhD student Imani 2008 which submitted his thesis in 2008, carried out nonlinear SSI analysis using what we call the CIFECM. CIFECM stands for consistent infinitesimal finite elements cell method for boundary, and used hybrid methods. Then Sarkar considered liquefaction for SSI analysis. In 2014, Saeed modeled the boundary using what we call SBFEM, scale boundary finite element method, and nonlinearity of soil using his model, soil model has been considered. Recently, very recently in Firoz 2023, who submitted his final thesis in March this year only, carried out 3-dimensional nonlinear soil interaction analysis for combined pile raft foundation for nuclear power plants. So, these are the work which has been done recently by our research group on soil interaction. I like to share with you some of the work, may not be possible in this lecture to share all the work, but few of the simple work. First, when we talk about modeling of boundary, it could be approximate modeling and it could be rigorous modeling, and I am able to work for both approximate as well as rigorous modeling. These boundaries are local in space and time, so they could be the elementary boundaries, the viscous boundary, Kelvin elements, transient transmitting boundary, infinite elements, there are so many. So, the work which has been done using Kelvin elements are shown here. For structures which are supported on pile foundations, then problem of SSI can be reframed and it can be treated as a soil pile structure interaction, that is SPSI, and response of an SPSI system, that is soil pile interaction system, can be again considered like sum of the kinematic interaction plus inertial interaction. And naturally this kind of treatment can be carried out only for linear analysis, where you are summing up two responses. For SPS system, SPS means soil pile structure system, two types of interactions effect need to be considered. One is soil pile interaction, wherein you are considering the pile group, that is pile soil pile for soil pile interaction for a single pile, while pile soil pile for a group piles, and foundation structure interaction need to be also considered. One of the the technique which we have initially developed in 2004 and which is published in Soil Dynamics and Earthquake Engineering Journal long back in 2004 is given here. Though it is linear analysis, but using a technique what we call the successive coupling scheme, we can carried out the nonlinear analysis also using this scheme. In this scheme what we do, you have soil pile structure system, and in this soil pile structure system you have the superstructure here, and at the base you have pile foundations. Now one way for direct methods of soil interaction, this whole system need to be considered together, and that is not a difficult task today, because now computation facility have developed like like anything. Now we are talking about 5G or so, but at that time the computer's speed was not so much, and carrying out the soil interaction analysis considering the whole structure and the foundation was difficult. So what has been done? We divide the system in two parts, one is called foundation subsystem and another is structure subsystem. And with this division we consider one system at a time for the analysis, but there is a continuous feedback from one system to another system. For example, for the time domain analysis, for when t time equal to delta t, that is the first step, you analyze the foundation subsystem, you apply some input motion at the base of the foundation subsystem, and then solve for what is the output at the top of the piles, that is up delta t for this case. Now when you consider the structure subsystem, then this is subjected to the motion which is due to the up delta t which you have found in this first step, and this is also subjected to your motion coming. So we analyze this system. Now in the second step, when you go for the pile foundations, then it is subjected to both input motion which is coming due to earthquake and the inertial load which is same Fp delta t, find out using the in the structural analysis or the analysis of the building in the first step. So the forces applied in the second step are earthquake motion as well as the forces which is found at the base of the piles, at the base of the columns or the top of the piles. And then for the second step we carried out for the buildings also, and this keep continuing. Now the success of this scheme will depends on how small you consider delta t. So for harmonic excitation we consider the delta t should be the less than Tp by 20, where Tp was the time period, and for time history analysis delta t may be already given to you. Normally for example delta t for many earthquakes is 0.02 second. So using this you find out the value of this you solve and find out the response of the system. Now using the successive coupling scheme we try to generate some results which is already published. One was for case for single pile, another was for case for 2 by 2 pile group. In case of single pile and 2 by 2 pile group, both are situated inside the soil. You have a pile here, single pile, and in this case 2 by 2 pile group. In the first case the structure is directly assumed as a lumped mass on the top of the pile. In the second case, you have two soil columns which are scattered away from both the piles, but ultimately load will be transferred on the pile cap. So, you have 2 by 2 pile group, and the spacing in between piles is important. So, the spacing considered between the piles is S by D equal to 5, whereas S is the spacing, center to center spacing between the piles, and D is the diameter of the pile. So, the dimensions are given here. Because it was a linear analysis and the load applied was also symmetrical. So, as a result we was able to use only the quarter model of the soil. So, rather than considering the full finite element model, which is computationally expensive. So, we consider 1/4 of the model, and for consideration of this, when you cut the model, then you need to consider what we call the axis of symmetry and axis of antisymmetry. So, you need to apply the conditions axis of symmetry and axis of antisymmetry, which is given here. For example, if I draw the plan of these models, it is plan here and the front elevation in this case. So, let us see in the plan, this is the boundary condition where rollers are applied, this is the boundary condition applied using axis of symmetry concept, and this is axis of antisymmetry. Once you apply these rollers, that means in 2D case you can move in the horizontal direction, but not in the vertical direction. But in this boundary at the sides, again you can move in the horizontal direction, but not in the vertical direction. So, these are the two boundaries, axis of symmetry and axis of antisymmetry. On cutting another boundary, you put the Kelvin elements, which consist of spring and dashpot. So, in the elevation, the location of the Kelvin elements is also shown, and you have the bedrock, and this is also cut down. So, this is axis of antisymmetry, which you can expect here. So, this work is already published in Canadian Geotechnical Journal in 2004. So, now what are the results? Let us discuss some of the results using effect of SSI on frequency response. So, the results are segregated in different steps. First, what is the effect on the free field response? Then what is the effect of response of single pile, that is soil pile interaction, then response of pile group, and finally soil pile structure interaction, that is the response of the complete system where you are considering the soil, pile as well as structure. So, here is effect of soil on free field response. So, you could see that the properties, the free field response is getting peak value at some particular frequency, but after that it is decreasing. So, in this case on y axis you have the normalized free field response. One thing is important here to note, that this normalized free field response is not a constant, rather it is changing with the frequency, and you get a peak value at some particular frequency, the peak is coming, and then after that it started decreasing, which could be seen in this case. So, this is the effect of SSI on free field response. That means there is no pile or the foundation on the system inside the soil. Now, if I insert the pile inside the pile group inside the soil, then the response which I get at the top will be considered as kinematic interaction, and in this case the effect of soil pile interaction is considered, and in this case there is a transfer function, that is the response at the pile head divided by the input motion. So, UG. So, you have the input motion here in this case, and that this difference in this case will be, the difference in this case is nothing but, this was input motion was u naught and UG was the normalized free field response. So, in this case y axis is normalized with respect to the amplitude of the input motion u naught, while in the second case this has been normalized with the UG, where UG was nothing but UG was found out in this step, first step. So, UG is known. So, in the second step then we have defined the transfer function UP divided by UG, where UP and UG are find out at the same point, but difference is that in case of UP piles was present, in case of UG it is free field motion. So, you could see that this transfer function is not unity, it starts from unit value, then it goes some peak value and then again come down. So, again there are certain frequencies where the response is peak. Now, we also carried out the analysis for the complete system, that is soil pile structure, pile soil pile interaction for a group, and for a group of piles you can see that the effect of S by D, that is the spacing ratio, is quite large. So, for example, in this result you have the real part and imaginary part for 4 types of cases. One is single pile, then in another case you have 2 by 2 pile group, but varying spacing between the pile group. So, you could see the single pile response is more or less flat, which is almost near to 1, and even for the damping case also. But as you go increase the number of piles, then it will depends on the spacing between piles. So, this was black line was for single pile, and other 3 are for 2 by 2 pile group with varying spacing. So, for the low spacing your behavior is quite different. That means, after a certain point it come like you will have the negative values, and that is there. While in case of S by D equal to 5 and 10, the peak values are happening at very different frequencies. So, that means what is the peak value, that will depends on case by case, whether the this negative stiffness may come when you have S by D equal to 2. Similarly, this was the case for stiffness. Same thing is for damping, which is given in the part B, which is shows the imaginary part, and you could see again the black line which is for the single pile, which is remains same, more or less same as before. So, this is work which is already, as mentioned, published in Canadian Geotechnical Journal. When we consider the total system, soil, piles, the piles like a foundation, and then superstructure building, what is the effect of SSI, which is given in this slide? You could see that there are lines which are, this line, red line is without interaction, and then these 2 are with interaction. That means without interaction means you are not considering the effect of soil as SSI. In that case your response acceleration factor shoots up like this, which you could see here. But when you consider the effect of interaction, then these values first of all come down from very large value to a finite value, which is coming here, and then start decreasing with the period or time frequency. So, this is the more real case then. So, effect of successive coupling on the response of pile and soil dynamics and earthquake engineering, it has been published. Now, modeling of boundary, we already discussed there are different types of boundaries. First one is the elementary boundary where you need to put rest end only, then local boundary where you use the viscous dampers, and the coefficient of these viscous dampers can be found out using these equations here, and this is for first one is for P wave, another one is the for S wave. So, this is, I think this should be Cp, P wave. So, using this equation you can find the damping coefficient. Then you have consistent boundary, where in case of consistent boundary spring and viscous dashboards in parallel is used to simulate a semi infinite region. For example, in this case dynamic stiffness is given by this relation G divided by 2 pi r naught S1 plus iota S2. In this case you have different conditions which we already discussed. One during dynamic soil property, here one you have is only with the rollers, that is rest end has been put. So, this will be treated, the first one will be treated elementary only. Then the second one is local boundaries. Third one is called consistent boundary. So, in this case the coefficient dynamic stiffness can be find out using these relations, which is for the springs. You have in this equation S1 plus S2, they are 2 dimensionless parameter, they are dimensionless parameter. So, in this case modeling of rigorous boundary has been done rigorously also using the concept of CFECM. It has been done by Imani and Maheshwari, published in Soil Dynamics and Earthquake in 2009. So, what has been done here, the interface is considered very near to the base of the structure, and in this case this is called CFECM, consistent infinitesimal finite element cell method. This is an alternative to the BEM. BEM we already discussed, that is boundary element method, which applies analytical solution to incorporate radiation damping. A cloning algorithm based on fully FEM formulation have been suggested by so and so Das Gupta, and Imani and Maheshwari use the CFECM boundary for the SSI problem and its application in pile foundation. So, here is the modeling of boundary again for the substructure system. What has been done here, whole total system is divided into two parts. One part where you do not have the piles, at the location of piles some excavation has been done, but in the second part which is for the near field, you consider that pile and pile cap together part of the soil, and we analyze the near fields, this case the second case, and then find out the spring and dashboard coefficients which are used in the design for the far field case, the first case. Then some work has been also done for considering soil interaction in liquefiable soils. Initial work was published by Finn and Fujita, which proposed the design and analysis of pile foundations in liquefiable soils. Later on, Liana Pathana and Polos in 2004 investigated the effect of nature of earthquakes and the assessment of liquefaction of soil deposit during earthquakes loading is carried out here. A significant parametric study on the influence of soil liquefaction on single degree of freedom system structure was performed. Sarkar investigated the 3-dimensional soil pile behavior under dynamic load condition for the soil with liquefaction. This is reported in these publications, Maheshwari and Sarkar, Sarkar and Maheshwari, so that you may go through if you are interested. These are the references, which are the key references which are used in the preparation of this presentation, and thank you very much for your kind attention.